In this presentation, we'll examine second-order systems, specifically their transient response, and this follows up to our study on first-order systems. So let's start with our definition of a second-order system that we'll consider. G of s equals b naught over s squared plus a1s plus a naught. We're going to convert this into a standard form, much like we did for first-order systems. For this conversion, we'll need to define a few constants. First, omega n, which is the undamped natural frequency. It will be equal to the square root of a naught. K, the DC gain which we've seen before, is b naught over a naught. And zeta is a1 over 2 square root a naught. And this is the damping ratio. With these defined, we can write g of s in the standard form that we'll consider. G of s equals k times omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. This form is very useful because it allows us to relate the transient behavior to these variables omega n, k, and zeta. Before going on to look at the transient response of second-order systems, let's see a few examples. So our first example is the mass spring damper system, which we've been studying quite a bit. We have a mass that's connected to ground through a spring and a damper. There's a force acting on the mass, and we're measuring its displacement, x. The spring stiffness is denoted k sub s, the mass m, and the damping coefficient c. Then the transfer function for the mass spring damper system is 1 over ms squared plus cs plus k sub s. So you can see this is a standard second-order system. I've labeled the spring stiffness k sub s since I didn't want to have this confused with the DC gain k that we'll be using in this presentation. The next second-order system that we'll study is an RLC network. This is a circuit where a voltage is applied to the terminals at the left end, and we measure the voltage across a capacitor at the right end. And in the circuit, there is an inductance labeled L, a resistor labeled R, and the capacitor labeled C. The transfer function between the input V1 and the output V2 is as follows: 1 over CLS squared plus CRS plus 1. So you can see this is also a second-order system. So now that we've seen some examples of second-order systems, let's turn our attention to the transient response. And we'll need to think about 3 cases. All of these cases correspond to stable second-order systems. That's the transient response we're most interested in. If the system was unstable, then of course the transient response would become unbounded. So here are the 3 cases that we're interested in. The first is where the damping factor zeta is between 0 and 1, and this is referred to as the underdamped case. The second case, zeta is equal to 1, and this is the critically damped case. And for the third case, zeta, the damping factor, is greater than 1, and this is referred to as the overdamped case. Depending upon which case we have, we'll have different arrangements of the poles in the left half plane. For the underdamped case, the poles are a complex conjugate pair. For the critically damped case, the 2 poles lie one on top of the other on the real axis in the left half plane. And for the overdamped case, case number 3, the 2 poles are distinct and on the real axis in the left half plane. In this presentation, we'll focus on the first of these three cases. That is the one of the underdamped second-order system. We'll focus on this case, since the behavior is quite different than the critically damped case or the overdamped case. Critically damped and overdamped systems behave much like first-order systems, but an underdamped second-order system shows behavior that first-order systems do not. On this page, I'm again showing the standard form for our second-order system. K omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. The poles of this transfer function are minus zeta omega n plus and minus j square root of 1 minus zeta squared omega n. The real part of the poles, we'll note, is minus zeta omega n, and the imaginary part of the poles is square root of 1 minus zeta squared omega n. Previously, we referred to square root of 1 minus zeta squared omega n as omega d, the damped natural frequency. So let's now look at the step response of an underdamped second-order system. The way we can find this is we'll start with the relationship between the input x of s and the output y of s through the transfer function k omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. And we'll substitute in x of s equals 1 over s. That, of course, is the Laplace transform of the unit step. We multiply these together to find y of s. Then we partial fraction expand and inverse Laplace transform. And the response is y of t equals k times the quantity 1 minus beta e to the minus zeta omega nt sine omega dt plus phi, all times u of t. And in this expression, beta is equal to 1 divided by the square root of 1 minus zeta squared. Omega d we encountered before. It's square root of 1 minus zeta squared omega n. And phi is the inverse tangent of the square root of 1 minus zeta squared divided by zeta. I'd like you to pay close attention to the form of the response to the unit step. First, note that the DC gain is on the outside of the terms here. The larger the DC gain, the larger the response. Second, I'd like you to note the term inside the curly brackets contains a term that has a decaying exponential multiplied by a sine wave. The sine wave is at a frequency of omega d. The rate of decay of the exponential is determined by zeta omega n. Let's now examine how the terms in the response contribute to the graph of the response. So I've written out y of t in a slightly different way than on the previous page. I've shown it as three terms. Term 1 is the steady state value, k. Terms 2 and 3 are multiplied together. The first is the decaying exponential, and the second is the sine wave at frequency omega d. Terms 2 and 3 combine together to make the transient. You'll note that term 2, the decaying exponential, dictates an envelope within which the sine wave moves, as shown in the figure above. You'll also note that as the transient decays, it will go to the value that is in term 1, that is k, the DC gain. Here are two aspects of the response I'd like to point out. The first is that beta sine of phi is equal to 1. And what this means is that y, the output, at time 0 plus, will be equal to 0. That is, there's no discontinuity in the response due to the step at time 0. This makes physical sense if we think about the output as, say, displacement of the mass, and the input as a step in force. The mass does not move instantaneously. It takes some time for it to move, so its position is a continuous function, even when a step input force is applied. The second item here is that we can define a time constant for the second order system response from the decaying envelope. It is the decaying envelope which will determine how quickly we reach steady state. And you can see the role of the time constant is given by 1 over zeta omega n, since it's this value that normalizes time in the exponential. Let us now look at the time response of the system to a unit step. We'll note, as labeled by 1, the decaying exponential, shown in blue, with a time constant t equals 1 over zeta omega n. We'll note the largest value of the response of y of t, and this is called the peak overshoot. The period of oscillation of the sine wave is given by 2 pi over omega d, where omega d is the damped natural frequency. The settling time, at which it falls within 2% of its final value, is about 4 times the time constant, t, and that point is labeled with the yellow arrow. All of these important attributes of the step response are related to the location of the poles in the complex plane. Let us start our discussion of these relationships. First, we'll note that the period of oscillation is related to omega d, and omega d is the imaginary part of the complex conjugate poles. Next, I'll point out that the rate of decay of the transient is related to the time constant. We found that minus zeta omega n was equal to minus 1 over t. So, since minus zeta omega n is the real part of the complex conjugate poles, we know that the real part of the complex conjugate poles is related to the rate of decay and to the time constant for the second order system. So we've seen that the imaginary part of the poles dictates the rate of oscillation, and the real part of the poles dictates the rate of decay. I want you now to note that the slope of a line through the poles extending from the origin is the square root of 1 minus zeta squared divided by zeta. That is, the slope of the line through a pole is dependent only on the zeta of that pole. This is important because the peak overshoot is only dependent upon zeta and the DC gain. We'll study the role of peak overshoot a little more in our next presentation. At this point, let's just examine how the peak overshoot changes with the damping factor zeta. And here is a plot of the normalized response. That is, we take y of t and divide it by the DC gain. That means the transient will always settle out to 1 in these plots. And now we're looking at the plots as a function of zeta. We have a curve for zeta equals 0 in green, for zeta equals 0.3 in blue, and for zeta equals 0.8 in red. And what you'll note is the overshoot, if there exists any, is very dependent upon the value of zeta.